what are biomolecules? Biomolecules are essentially organic molecules. Okay, they take part in the metabolism of animal and plant bodies. Okay, what are biomolecules? Biomolecules are usually organic molecules. Okay, essentially organic molecules. Okay, biomolecules are organic molecules that take part in the metabolism as well as in the catabolism of plant and animal body. Plant and animal bodies. Okay, so this is the basic definition of biomolecules. Biomolecules are organic molecules, essentially organic molecules that take part in the metabolism of plant and animal bodies. Okay, now which are all the molecules, okay, comes under biomolecules. Okay, so in biomolecules, we have carbohydrates, we have proteins, we have nucleic acids, then we have vitamins. Okay, these are the molecules, right, which we call as biomolecules. Okay, carbohydrates, proteins, nucleic acids, and vitamins. Okay, these are basic biomolecules. Now, what are their roles actually, right? What they do in the animal body as well as in plant body. Carbohydrates, we call them carbohydrates as energy producers. Carbohydrates are energy producers, right? They produce the necessary energy for the body, okay, for the body to function. Okay, so they are energy producers. What are proteins? Proteins are body builders. Right? Okay, our not only animal body, even plant body, right? They are made up of essentially proteins, right? So proteins are body builders. Nucleic acids, they are organic molecule, right? They transport the information from one person to the other person, okay, or from mother to children, like that. Okay, so it is actually hereditary, or they transport, right? They transport the information. Okay, so RNAs, DNAs, we are going to discuss everything. RNA, DNA, right? These molecules, right, are usually called as nucleic acids. They transport genetic information, right? They transport genetic information. Right? Not only that, they are also having some other role. Okay, they also involve in the synthesis of some proteins, right? Yeah. one second, students. There's a power cut. Just a minute. Right. Nucleic acids are molecules which transport genetic information. Okay. Then vitamins are molecules which regulate our body function. Right. They are body regulators. Body regulators. Okay. Body regulator means they make the function, right? They make the functions normal, right? So vitamins are molecules which regulate the body function, right? So this is very, very important. And apart from this, we also have minerals, right? Lipid molecules, other molecules also there, but these are essential biomolecules which we are going to discuss, right? Now let us start with the carbohydrates first. So remember, carbohydrates are molecules which produce necessary energy to the body. Okay, they are energy producers, right? So let us start with the carbohydrates. So remember, these are the four molecules. Even some more molecules are there, lipid molecules and some minerals also there. Okay, which I have not included because it is not necessary for us to discuss everything. Okay, as in our syllabus we have only these three molecules: carbohydrate, proteins and nucleic acids. Even vitamin is not there, right? Okay, so let me start with the carbohydrates. Carbohydrates. Okay, so as I told you before, carbohydrates are energy producers. Okay, and from the name itself, see, carbo means carbon, hydrates mean water molecule. So in those days people thought that carbohydrates are hydrated carbon atoms. Simply you can say like that, they are hydrates of carbon. What is meant by that? You take carbon, to this you add some number of molecules, but it was found that if you have n carbon atom, there exists n number of water molecules. Okay, if you have water molecule, it is called hydrate. Hydrates of carbon, okay, it is called as carbohydrates. So in those days people thought that carbohydrates are molecules which consist of which obey this formula. That's why they called the compound as carbohydrates. Okay, yeah, many carbohydrates follows this formula. For example, I'll take glucose. The formula for glucose is C6H12O6. So there are 6 carbon atoms, and you can write this H2 hydrogen and oxygen as H2O 6 times. Correct? See, we have 6 carbon atom, we have 6 into 2 12 hydrogen, and 6 into 1 6 oxygen. So you can write glucose, you can write fructose, right? Most of the carbohydrate, the molecular formula of carbohydrates obey this formula. That's why they called these molecules as carbohydrates. But later it was found that few molecules or some molecules which are not carbohydrates, okay, but they also obey this formula. For example, you take acetic acid. Okay, the formula of acetic acid is CH3COOH. Acetic acid is not a carbohydrate. Okay, acetic acid is not a carbohydrate. It's not a carbohydrate. But see the formula, you can write this acetic acid molecular formula as, so we have 2 carbon atoms, C2. We have 4 hydrogen, so I can combine that as H2O twice. Okay, see that we have 2 carbon, right, and we have 4 hydrogen, here 3, here 1, 4 hydrogen, and we have 2 oxygen. So even acetic acid molecule can be written like this. Okay, that means you can say that acetic acid also has hydrates of carbon. Okay, but acetic acid is not a carbohydrate. So this formula, though it is called as general formula for carbohydrate, but many molecules which are not carbohydrate, they also obey this formula. And some carbohydrate, students listen carefully, some carbohydrate, right, they have formula like this. See, deoxyribose, right, the formula is C6H12O5. There are carbohydrates having this formula. Okay, we call this as deoxyribose. This deoxyribose, right, okay, it doesn't follow, right, this formula CnH2n, CnH2ON, right, it doesn't follow this formula, right, it doesn't follow this formula. So some molecule which are not carbohydrate, they follow this formula. Some carbohydrates which are not some carbohydrates, they do not obey this formula. Therefore this name, that is you can define carbohydrate as hydrates of carbon. Okay, that definition is not absolutely correct. Okay, because in some cases it is changing. Therefore what we are going to do is, so this definition is insufficient. Okay, that is carbohydrates, though it is generally called as hydrates of carbon, okay, hydrates of carbon, that name is not sufficient, that definition is not sufficient. Okay, so what is the latest definition given by scientist, okay, chemist very specifically? Okay, the latest definition is this. What is the definition for carbohydrate? So students, keep this in mind. The name carbohydrate came because of this formula only. Okay, so people thought that carbohydrates are hydrates of carbon. In those days, people say that carbohydrates mean simply hydrates of carbon. But yes, so many carbohydrates obey this formula. But later people found that few molecules which are not carbohydrate, they obey this formula. Similarly, carbohydrates, some carbohydrates, they do not obey this formula. Therefore defining carbohydrates as hydrates of carbon is not sufficient. Therefore scientists have given a new definition for carbohydrates, right? The new definition is this. What is that? What are carbohydrates? Carbohydrates are optically active. I'll write here. Usually they are optically active, polyhydroxy, optically active polyhydroxy aldehydes, optically active polyhydroxy aldehydes, or polyhydroxy ketones. I repeat, optically active polyhydroxy aldehydes or polyhydroxy ketones, or any other compounds, or compounds which produce these molecules, that is polyhydroxyaldehydes and polyhydroxy ketones. Any other compounds, or any compounds which produce such molecules, right, which produce such molecules. Such molecules here means polyhydroxyaldehydes and polyhydroxy ketones, right? Any compounds which produce such molecules, molecule, right, on hydrolysis. Okay, if you hydrolyze some compounds, they produce polyhydroxyaldehydes and polyhydroxyketones. Those compounds are also called as carbohydrates. So what are carbohydrates? The definition is this: optically active polyhydroxyaldehydes or polyhydroxyketones or any compounds which produce such molecules on hydrolysis are called okay, carbohydrates. Carbohydrates. This is the latest definition given by a chemist, right? Optically active. I'll tell you what's the meaning for optically active and all. Optically active polyhydroxyaldehydes or polyhydroxyketones or any compound which produce such molecules on hydrolysis are called carbohydrates. Okay, that's the meaning for, that's the definition, right? Proper definition for carbohydrates. Now, what is the meaning for optically active? First, let me take this word. What is the meaning for optically active? It's very simple. What is the meaning for optically active? Optically active compounds or molecules. When we can say a molecule is optically active molecule, what is the meaning? Students, very simple. You take some solvent, water or any solvent. Okay, you take some solvent, right? Then you take any molecule for which you are going to study whether the molecule is optically active or not. Suppose in this case I'll take carbohydrates, right? I'll take carbohydrate. It's not necessarily carbohydrate. You can take any molecule. If you want to check whether the molecule is optically active or not, you take the compound, dissolve the compound, okay, in a solvent, right? You can take water, you can take alcohol, right? Any solvent. Okay, so you take your molecule, dissolve the compound in water, then you pass plain polarized light, plain polarized light. What is meant by that? Light which vibrates only in one plane. Okay, the plane of vibration occurs in only one plane. If light vibrates only in one plane, we call the light as plain polarized light. So you pass the plain polarized light through the solution. If the solution that is coming out, transmitted light, if the plane of the vibration changes, okay, the plane, say for example, if you see from this side, right, suppose if the plane appears like this, right, then after passing through the solution, if the plane changes, right, it may rotate in the clockwise direction or it may rotate in the anti-clockwise direction, whatever maybe it is. Okay, so if you see from this direction, the plane will appear like this, appear like a vertical line, right? After passing through the solution, if the plane rotates in clockwise or anti-clockwise, then we can say that the compound is optically active. So what are optically active compounds? Simple. Compounds which optically active compounds are compounds which rotate the plane polarized light. Simple. Compounds which can rotate plane polarized light are called optically active compound. It may rotate in clockwise or it may rotate in anti-clockwise. That is different. Okay. If it rotates in clockwise, we call the molecules as, we represent those molecules with the symbol plus. Plus means clockwise rotation. Minus means anti-clockwise rotation. Right? Anti-clockwise. So don't worry about this plus and minus right now. Just keep this in mind. What is the meaning for optically active molecule? If any molecule rotates the plane polarized light in clockwise direction or anti-clockwise direction, we call those molecules as carbohydrate. Okay, so we call the molecule as optically active molecule. Here I took carbohydrate as an example, right? So this is the idea now. So what is the meaning for optically active? Optically active means the compounds having the tendency to rotate the plane polarized light. Okay, then let me come to the next word, polyhydroxy. What is meant by that? What is meant by polyhydroxy? Poly means many, hydroxy means OH group. So if a compound contains many OH groups, right? Polyhydroxy. What is the meaning for polyhydroxy? Polyhydroxy means compounds which contain many OH group. Polyhydroxy, right? Poly means many. Okay, more than one, right? You can say more than one. Hydroxy means OH groups. OH groups. If molecule contain many OH groups, more than one OH groups, we call those. We say that the molecule consists of the molecule is a polyhydroxy molecule. Okay, polyhydroxy means more than one OH group. Okay, then so polyhydroxy, aldehydes are polyhydroxy ketones. You know very well, aldehydes consist of this functional group C double bond OH, or we write simply CHO, right? And remember student, aldehyde always present at the terminal position. Okay, it's right in carbohydrates, right? Essentially in carbohydrate they present at the terminal position. Okay, aldehydes. Okay, this is aldehyde. Aldehydes have this functional group. Okay, and what are ketones? Ketones, right? They are aldehydes. Ketones, they have this functional group C double bond O group. Okay, this keto group, CO group, does not present at the terminal carbon. Students, keep this in mind. Aldehyde always present at the terminal carbon, whereas keto group is present, okay, in between, right? It may present in second carbon or third carbon, like that. In between, it never present in terminal carbon, right? So that's a basic thing you should keep in mind, right? So what is the definition? The definition is this: carbohydrates are optically active. Optically active means they can rotate plane polarized light. Polyhydroxy means many OH group. Okay, aldehydes. Aldehydes means they contain CHO group. So any organic compound containing aldehyde functional group with many hydroxy group and optically active, we can say that they are carbohydrates. Similarly, organic compound containing keto group with many hydroxy functional groups, and they can rotate the plane polarized light, we can call them as carbohydrates. Okay, so this is the basic definition, right, or the absolute definition of what is called the carbohydrates. Right, now proper definition. Okay, now okay, how to classification. How to classify carbohydrates. Okay, there are many ways of classifying carbohydrates, but I will give you some in a flowchart manner so that you can easily understand this, right? Yeah, students, keep this in mind. We call carbohydrates also as saccharides. Okay, if wherever the saccharide name is present, okay, you can immediately say that they are carbohydrates, right? Carbohydrates contain the term saccharides. Saccharides means carbohydrates. Now we classify carbohydrate we classify carbohydrate basically into two, right? Sugars and non-sugars. Sugars and non-sugars. We classify carbohydrate basically into two, sugars and non-sugars, right? Yeah, what are sugars? Sugars. Using some characteristic property, you can say that the molecule is sugar or non-sugar. What are the characteristic property? Sugars are molecules which produce the sweet taste. They produce sweet taste. Usually they produce sweet taste. Then sugars are molecules which are freely soluble in water, or readily soluble in water. They are soluble in water. Second point. And third important is, sugars are usually crystalline in nature. Sugars are molecules which are crystalline in nature. Okay. So if molecule, suppose you have a carbohydrate, you want to know whether it is sugar or non-sugar, what you have to do, you just check these characteristics. Okay. If it produces sweet, or if it's readily soluble in water and crystalline in nature, then you can call those carbohydrates as sugars. What are non-sugars? Non-sugars are molecules which usually do not give any sweet taste. Okay, no sweet taste. No sweet taste. Okay, non-sugars. Then they are usually insoluble in water. Insoluble in water at room temperature. At room temperature, some non-sugars may be soluble at high temperature. Okay, in hot water they may be soluble, but in cold water they are usually insoluble, right? So I'm giving this information based on room temperature. Okay, so in normal water at room temperature, right, the non-sugars are insoluble in water. Then third point, they are usually amorphous. They are amorphous in nature. Okay, powdery. Amorphous in the sense I'm saying that the molecules appear like powder. Okay, they are powdery in nature. So these are only some of the characteristics of non-sugars. So if you want to know whether a carbohydrate if you want to know whether a carbohydrate is non-sugar or not, what you have to do, you check these characteristics. Okay, whether they produce sweet taste or not. See, if they do not produce sweet taste, if they are insoluble in water and it appears like powdery substance, amorphous, right, we can say that those carbohydrates as non-sugars. Okay, now non-sugars are also called as polysaccharides. Polysaccharides, right? Non-sugars are also called as polysaccharides. We'll discuss that later. Okay, before that we'll finish off the sugars. Okay, so sugars are carbohydrates which have sweet taste, soluble in water and crystalline in nature. We can classify sugars into two. We can classify sugars into two, right? Monosaccharides and oligosaccharides. Okay, we can classify these sugars into two, monosaccharides and oligosaccharides. What are monosaccharides? Monosaccharides are molecules which do not monosaccharides are carbohydrate molecules which do not undergo further hydrolysis. Simple. Monosaccharides are carbohydrates. Okay, they do not undergo hydrolysis. Okay, we call them as monosaccharides. What are oligosaccharides? Oligosaccharides are carbohydrates which on complete hydrolysis produce 2 to 10 monosaccharide units. Okay, so here monosaccharides do not undergo, let me write blue pen, monosaccharides do not undergo hydrolysis. They do not undergo hydrolysis. What are oligosaccharides? Oligosaccharides, okay, undergoes hydrolysis. Okay, undergo hydrolysis, okay, and produce 2 to 10 monosaccharide molecules or monosaccharide units. Monosaccharide units. What is meant by that? Listen, you take one molecule of carbohydrate, right? So just for understanding purpose, I am saying like this. You take one molecule. Of a carbohydrate, one molecule of carbohydrate, and then hydrolyze it. Carry out hydrolysis. Hydrolyze. Okay, you just carry out hydrolysis. If one molecule of carbohydrate on hydrolysis produce 2 to 10, 2, 3, 4, 5, 6, 2 to 10 monosaccharid units. 2 to 10 monosaccharides, right? Then we call this carbohydrate as oligosaccharide. Students, keep this in mind, very, very important. Monosaccharides do not undergo hydrolysis, simple. What are oligosaccharides? Oligosaccharides are carbohydrates which undergo hydrolysis and produce 2 to 10 monosaccharide units. What is the meaning for 2 to 10 monosaccharide? Simple. If you take one molecule of carbohydrate and if you carry out hydrolysis, they will produce 2 to 10 monosaccharide units. Some carbohydrate may produce 2 monosaccharide. Some carbohydrate on hydrolysis may produce 3 monosaccharides. Some carbohydrates may produce 4, may produce 5. Some carbohydrates may produce even 10. Okay, those carbohydrates are called as oligosaccharides. Okay, so keep all these things in mind, very, very important. So we classify carbohydrates into sugars and non-sugars. Under sugar, okay, we have 2 monosaccharides and oligosaccharides. Okay, now we'll discuss. We'll see further classification of monosaccharides. This monosaccharide is further classified into 2. Let me write here. Monosaccharides are further classified into 2. Okay, based on the functional group that is present. Right? In some monosaccharide, you may have aldehyde group. In some monosaccharide, you may have keto group. Okay, if aldehyde group is present, if monosaccharide contains aldehyde group, we call those monosaccharides as aldoses. Aldose, singular. Okay, aldose. If monosaccharide contains keto functional group, keto group, we call those carbohydrates as ketos. Students, this is another important point you should keep in mind. Wherever you see the suffix os, O-S-E, os, right, that is a carbohydrate. Okay, if you see the suffix os, okay, glucose, mannose, fructose, right, the suffix os, right, indicates a carbohydrate. Okay, if any organic compound contains the suffix os, we can say that this carbohydrate. Right? Now, so in monosaccharide, we have 2 aldose and ketose. Aldose consists of aldehyde group, functional group, and ketose consists of keto functional group. Okay? Right. In aldose, depending upon number of carbon atoms present, okay, suppose I have a monosaccharide which consists of aldehyde group, okay, and depending upon number of carbon atom present, you can call them as triose, tetrose. Okay, suppose if 3 carbon atom is present, we call them as aldotriose. Aldose means since it is coming under aldose, I am using the term aldotriose. Triose means 3 carbon atom. 4 carbon atom. If any aldose contain 4 carbon atoms, we say that it is aldotetrose. Aldotetrose. Right? What about 6 carbon, student? Suppose an aldose contains 6 carbon.
Aldohexose.
Aldohexose, that's all. So aldotriose, aldotetrose, aldopentose, aldohexose. Okay. Similarly, in ketose, if any ketose contain 3 carbon atom, we call them as ketotriose. Ketotriose. 4 carbon atom, ketotetrose. Tetrose. Ketotetrose. Similarly, 5 carbon atom, ketopentose. Okay. So depending upon number of carbon atom, you can call them as triose, tetrose, pentose, hexose, like that. Okay. Take note. So this is how we classify carbohydrates. This is how we classify carbohydrates. Okay. I'll repeat. Carbohydrates are also called as saccharides. We classify carbohydrates into 2, sugars and non-sugars. Sugars, will characterize, or will, based on some characteristic property, you can say that a molecule is sugars or not. Sugars are carbohydrates which produce sweet taste, which are soluble in water, readily soluble in water, and they appear as a crystalline substance. Okay, these are all some of the characteristic properties of sugars. What are non-sugars? They do not produce sweet taste. They are insoluble in water. Okay, insoluble in water in the sense they are insoluble at room temperature. Okay, then they appear like a powdery substance, right? Are amorphous. They are amorphous. Okay, so non-sugars are also called as polysaccharides. Okay, then the sugar molecules are further classified into 2, monosaccharides and oligosaccharides. What are monosaccharides? Monosaccharides are carbohydrates which do not undergo hydrolysis, right? Whereas oligosaccharides are carbohydrates which undergo hydrolysis and produce 2 to 10 monosaccharide units. Okay, 2 to 10 means 1 molecule of carbohydrate on hydrolysis produce 2 to 10 monosaccharide units. Okay, yeah. If okay, then I'll come to this little later. These monosaccharides are further classified into 2, okay, based on the functional group present. If it contains aldehyde functional group, we call them as aldoses. Aldoses means plural, aldoses. If it consists of keto functional group, we can call them as ketoses. Okay, in aldoses, depending upon number of carbon atoms, you can call them as if it contains 3 carbon atom, aldotriose, 4 carbon atom, aldotetrose, aldopentose, aldohexose, etc., etc. Okay, this is aldohexose. 6 carbon atom means aldohexose. Similarly, depending upon a number of carbon atoms, these ketoses can also be called as ketotriose, ketotetrose, ketopentose, etc. Right? Yeah. So this is the classification of carbohydrates. Then in oligosaccharide, we'll discuss this little later. In oligosaccharide, keep this point alone in mind. Carbohydrate, if it produces 2 monosaccharide unit, we call those oligosaccharide as disaccharide. I repeat, if 1 molecule of carbohydrate produce 2 monosaccharide units, we call those oligosaccharide as disaccharides. If 1 molecule produce 3 monosaccharide units, we call those carbohydrate as trisaccharide. So disaccharide, trisaccharide, let me write here. Disaccharide, trisaccharide, right? Tetrasaccharide, etc., etc. Disaccharide means 1 molecule of carbohydrate produce 2 monosaccharide units on hydrolysis. Trisaccharide means 1 molecule of carbohydrate produce 3 monosaccharide units on hydrolysis. That's the meaning for trisaccharide. So we have disaccharides, trisaccharides, tetrasaccharide, pentasaccharide, etc., etc. Okay, if it produces 10 monosaccharide units, then it is a deca, right? Decasaccharides. Yeah. So these are all the points you should keep in mind under classification, okay, of carbohydrates. Then, what are polysaccharides then? As per definition, if one molecule of carbohydrate produce more than 10 monosaccharide units, as per definition, right, more than 10 monosaccharide units, we call them as polysaccharides. But actually, the examples that we have, right, if you hydrolyze the molecules, they produce more than 100 usually. They produce more than 100 monosaccharide units. So polysaccharides are carbohydrates which produce many monosaccharide units, more than 10. For definition's sake, I can say like that. Polysaccharides are carbohydrates which produce more than 10 monosaccharide units on hydrolysis. Okay. Right. Now, so this is the classification of carbohydrates. Okay. Now, okay, we'll start with the monosaccharides first. Monosaccharides. Monosaccharides, I have told you already. Monosaccharides, I'll just write M means monosaccharide here. Monosaccharides are carbohydrates. Monosaccharides are carbohydrates which do not undergo, okay, monosaccharides are carbohydrates which do not undergo hydrolysis. Which do not undergo hydrolysis. This is a simple definition for monosaccharides. Monosaccharides are carbohydrates which do not undergo hydrolysis. What's the meaning? The meaning is, suppose, just for understanding purpose, I'll say like this. Suppose you take one molecule, of carbohydrate, any carbohydrate. Okay, if you want to say whether the carbohydrate is monosaccharide or not, you take one molecule, carry out hydrolysis. Just for understanding purpose, I am saying one molecule. Okay, but usually we take 1 mole like that. Okay, you take one molecule of carbohydrate, carry out hydrolysis. If the molecule remains as such, okay, if number remains as such, then the molecule is called monosaccharide. Number as well as the compound, whatever compound that you take, that compound remains as such. Okay, number remains as such. Not only that, the identity of the molecule also remains as such. Okay, so we call these molecules as monosaccharides. Right, very simple. Monosaccharides are molecules which do not undergo hydrolysis. Right? Yes, we have lot of examples actually. We have lot of examples. I'll give some standard examples. You might have already heard about that. Glucose, right? Fructose, okay, ribose, right, etc., etc. Many examples are there. Glucose, the formula is C6H12O6 glucose. Fructose also have the same formula, C6H12O6. Okay, see these glucose and fructose, these two molecules, they have same formula. Okay, ribose consists of 5 carbon atom, C5 H10O5. This is ribose. Okay, and remember students, you know very well, if two compounds have same molecular formula, we call them as isomers, right? if two different molecules, if two different molecules have same molecular formula, we call them as isomers. But in what way they differ, right? Actually, if you see the structure of glucose and fructose, okay, glucose consists of aldehyde functional group and fructose consists of keto functional group. Okay, if two molecules which are isomers, if they differ in the functional groups, we call them as functional isomers. Functional isomers. Students, keep this in mind. Glucose and fructose are called functional isomers. Why? Because glucose contain aldehyde group. Glucose contain aldehyde functional group, whereas fructose contain keto functional group. Keto. Okay, so functional groups are different. They have same formula, but functional groups are different. Therefore, we call them as functional isomers. Glucose and fructose are called functional isomers. Okay. Then we have ribose, we have arabinose. Many examples are there. I have given only few here, etc., etc. Okay. Yeah, these are all examples for monosaccharides. They do not undergo hydrolysis here. Okay, glucose, fructose, ribose, arabinose, right, xylose, lixose, many examples are there. All these are monosaccharides. Okay, now students, this is the simplest carbohydrate. Okay, or aldose. Let me take aldose first. Under monosaccharide, I'll take aldose first, then we'll discuss ketose. I'll give a few examples with their structure. Okay, before going to see structure, students, keep this in mind. If carbon atom attached with 4 different groups, carbon valency is 4, that you know. If carbon atom attached with 4 different groups, say here are different atoms. Say I have some group here A, some group here as B, some group D, some group E. So to the carbon atom, I have 4 different groups or 4 different atoms. It should be different, that's all. Then we can call this carbon, if carbon atom attached with 4 different atoms or 4 different groups, we can call this carbon as asymmetric carbon. Asymmetric carbon, also called chiral carbon. Chiral carbon. Asymmetric carbon or chiral carbon. Okay. And you know very well, these 4 bonds, right, are orienting in space and give you a tetrahedral structure. So around this carbon, the 4 bonds are orient in such a manner that they will produce tetrahedral structure around the carbon. So it is a 3-dimensional molecule, right? Carbohydrates are 3-dimensional, but we have to represent them on a paper. Paper is 2-dimensional, right? So for this, okay, a scientist gave a method to represent the molecule on his paper. Okay, so just put a plus symbol. Students, keep this in mind. If you put a plus symbol, then that center point consists of what is called the chiral carbon. You need not write carbon hereafter. If you just put a plus symbol, right, that the middle point consists of or the crossing point consists of chiral carbon. Then you can attach the 4 group. For that you have certain rules. Okay, right now you need not worry about that. The point that I like to say is, if I put a plus symbol like this, then that crossing point represent a chiral carbon. What is a chiral carbon, student? Student, what is a chiral carbon?
Carbon having 4 different functions.
Yeah, good. Carbon attached with 4 different atoms or 4 different groups. Okay, it is called chiral carbon. Good. Now, students, now tell me, in this structure, how many chiral carbon atoms are there? Suppose if I write like this, how many chiral carbon atoms are there?
3, sir.
Yeah, this is one chiral carbon, this is one chiral carbon, and this is one chiral carbon. We have 3 chiral carbons. This method of representing a molecule is what we call as Fischer projection. Fischer projection. Fischer projection. Okay, scientist Fischer introduced this method, so it is called Fischer projection. Fischer projection is nothing but representing a 3-dimensional molecule, right, on as a 2-dimensional one, or in 2-dimensional sheet. Okay, take down. Now, so each of this crossing point indicate a chiral carbon. Okay, now I will write the formula for glucose. Okay, let me start with like this. Glucose. Glucose 1, 2, 3, 4. Here we have aldehyde functional group, terminal carbon. I have told you aldehyde group present always at the terminal position in carbohydrates. Okay. If it is aldose, it consists of aldehyde group. That aldehyde group always present at the terminal position. Right. Now tell me how many chiral carbon atoms are there, students? In this structure, how many chiral carbon atoms are there?
4, sir.
4 chiral carbon atom. Yes, you're right. This is a chiral carbon. This is a chiral carbon. This one is another chiral carbon. This one is another chiral carbon. So we have 4 chiral carbon, right? And that in this terminal position we have a CH2OH group. CH2OH group. Okay. And in the other chiral carbon, right, I am going to give you the proper structure. Okay. This is carbon number 1, and this is carbon number 2. This is 3, 4, 5, 6. So in glucose we have totally 6 carbon atom. In the second carbon, in the Fischer projection, we should put the OH group in the right hand side, in the second carbon. This is the what I am writing is the proper structure of glucose. Okay. Then in the third carbon, OH group should be in the left hand side. In the fourth carbon, OH group should be in right hand side. Fifth carbon also OH group should be in the right hand side. Only in the third carbon, OH group present in the left hand side of Fischer projection. Okay, this is the structure of glucose. Take down. Is this clear, student? Any doubt?
No, sir.
Yeah, take down. See, in this molecule, this terminal position is aldehyde. This terminal position is some alcohol, primary alcoholic group is there, primary alcoholic group. Okay. So terminal groups are different. Okay, in an organic chain, if terminal groups are different, we say that it is unsymmetrical molecule. We say that the molecule is unsymmetrical. So glucose is an unsymmetrical molecule. In unsymmetrical molecule, okay, here we have 4 chiral carbon, right? Each chiral carbon, right, depending upon the chiral carbon present, you have many number of optical isomers, right? How many optical isomers are possible for this particular structure? Okay, number of optical isomers, number of optical isomers. The formula is this, 2 power n. For unsymmetrical molecule, this is the formula. If the molecule is unsymmetrical and if it contains n chiral carbons, so here n represent number of chiral carbon, n represent number of chiral carbon. Okay, the molecule is unsymmetrical. Unsymmetrical means this is the formula we use to find the number of optical isomers. So number of optical isomers equal to 2 power n. Okay, where this n represent number of chiral carbon. Now students, tell me how many optical isomers are possible for glucose? Yes, students?
2 power 4, sir.
2 power 4. 2 power 4, how much? 2 into 2 into 2 into 2.
32, sir.
Calculate correctly.
16, sir. 16.
Right? Yeah. 16 isomers, right? 16 optical isomers are possible for this glucose structure. Okay. For this structure, we have 16 possible isomers exist. Right? All are optical isomers. Right? Take down. So for glucose, we have 16 isomers. Take down. Now let me give you the structure of ribose. Let me write in the next page. Ribose. The structure of ribose is this. Ribose also an aldose. Okay, ribose also an aldose, and it consists of, yeah, how many chiral carbon atoms are there, students?
3, sir.
3 chiral carbon atoms. Very good. Right? And here in ribose, all the OH groups are present in the right hand side. Okay, in Fischer projection, if you write, okay, if you write OH group in right and left, right, they have some specified meaning. Okay, you cannot change just like that, right? It should be like this only. This is the proper structure of ribose. Okay, take down. It's called ribose. This molecule is called ribose. Okay, students, another important point I like to say here. Here the number, okay, how to give numbering for IUPAC name, you know very well. We always start with from the functional group containing carbon. So here the functional group is aldehyde. Aldehyde should contain the number 1, or should take the number 1. This is number 2, 3, 4, 5. So this molecule consists of 5 carbon atom totally. Right? So it is an aldopentose. Am I right, student? It consists of aldehyde group and 5 carbon atoms. So it is an aldopentose. Now listen, students, observe this carefully. First you tell me how many optical isomers are there. Number of optical isomers. Is it symmetrical? Is the molecule symmetrical, students? Is the molecule?
No, sir.
No. Yeah. This in this terminal group we have aldehyde, and here we have alcohol group, some primary alcohol group. So they are not symmetrical. It is unsymmetrical. For unsymmetrical molecule, number of optical isomers can be calculated using the formula 2 power n. What is n here?
3, sir.
Number of chiral carbon, yes, it is 3. Very good. So 2 power 3, yes, how much? 2 power 3?
8, sir.
Yeah. So 8 optical isomers are possible for ribose. Okay. Now students, this is very, very essential point. See here, which is the highest number chiral carbon? Highest number chiral carbon?
4, sir.
4, right? So 2, 3, 4 are chiral carbon. Among this, the highest number chiral carbon is 4. In highest number chiral carbon, in the Fischer projection, in which side OH group is present? Right hand side or left hand side?
Right, sir.
Right hand side, right? Students, keep this in mind. In Fischer projection, okay, in the highest number chiral carbon, if OH group is present in the right hand side, we call that structure or that configuration, we call them as configuration. We represent that configuration with the symbol D, capital D. Capital D gives you the configuration. Configuration. Right? When we should give the symbol D? In the Fischer projection, in the highest number chiral carbon, if OH group is present in right hand side, we should represent that as D. So it is a D ribose. Okay, D ribose. This D symbol, we use actually D symbol or L symbol. D and L symbols, okay, they represent configuration. They represent configuration. They do not have any connection with the optical activity. They do not have any connection with the optical activity. Students, I have told you in the beginning, plus sign indicate clockwise rotation. If molecule rotate the light in clockwise, we use plus sign. If molecule rotate the plane polaris in anti-clockwise direction, we use minus sign. Listen, instead of plus sign, you can also use small d. Instead of minus sign, you can also use small l. Listen, small d, small l, they have relation with the optical activity. Small d means rotation in clockwise, small l means rotation in anti-clockwise, but capital D, capital L, there is no connection between capital D and small d. There is no connection between capital L and small l. They are not same. They are different actually. Small d, small l represent optical activity. Whether the plane polaris light rotate in clockwise or anti-clockwise, we use D and small L symbol. Whereas capital D, capital L symbol, okay, is given only for the structure, only for the configuration. Okay, students, very important point. Just by seeing the structure of molecule, no one can say whether the molecule rotate light in plane polaris light in clockwise or anti-clockwise. Just by seeing the structure of molecule, one cannot say whether the molecule is optically active or not. One cannot say. It's a difficult one, because optical activity, it is an experimental property. Optical activity is purely an experimental one. Okay, experimentally you have to say whether molecule rotate light or not, but just by seeing the structure, you cannot say. You cannot say. Right? Yeah. Is this clear, student? Any doubt?
Yes, sir.
So remember, capital D and capital L, they do not have any connection with the optical activity. They represent just configuration. If OH group is present in left hand side, here OH is present in right hand side. If it is present in left hand side, we should use the L symbol. L. Okay. Now tell me, what about the glucose? What about this glucose? See the highest number chiral carbon. Which is the highest number chiral carbon here?
5, sir.
5. So in the highest number chiral carbon, in Fischer projection, OH group is present in right hand side. Therefore,
D right.
we should call this as D glucose. You're right. This compound is called D glucose. Okay, it's very, very important. Then I'll just give one example for ketose, then I stop. We'll continue this in the next class. Okay. CH2OH, CH2OH, C double bond O, 3, 4, 5. This is the proper structure of fructose. Proper structure of fructose. Okay, I have given structure of fructose in Fischer projection. Fischer projection. Okay, and this is keto group. Keto. Students, you can also write like this. You can also write the structure like this: CH2OH. See here, second carbon, third carbon CHOH. I'm sorry, third carbon OH left hand side, right hand side. Okay, fourth carbon fifth carbon, sixth carbon. You can also write like this, but this is not Fisher projection. Students, be careful in this. This is not Fisher projection. Fisher projection means chiral carbon atom should be represented with the plus symbol. This is Fisher projection. Here also you can write carbon, nothing wrong in it, CO. Fisher projection means chiral carbon should be represented with the plus symbol. Only in Fisher projection, okay, you can say whether the structure is D or L. With this structure you cannot say. You should not say actually. Right? I'm saying that some people are doing this mistake. In this structure they are saying that OH group is present in right hand side, so it is D. No. With this structure you cannot say. Okay, this is fructose structure, I agree. Okay, nothing wrong in it, that's correct. It's a fructose structure, but if you want to say the configuration D or L, then you must consider, or you must take only the Fisher projection. In Fisher projection, right, if OH group is present in the right hand side of the terminal chiral carbon, correct? How many chiral carbon atoms are there, student?
3, sir.
3 chiral carbon, right? 1, 2, and this one 3. 3 chiral carbon. So number of optical isomers? Is it symmetrical, students?
Yes, sir.
No. Terminal groups are same, I agree. But here I have keto group. This side I don't have keto group, right? Symmetrical means, okay, the structure should be from the middle. From the middle, right? The top group and the bottom group should be same. Right? To identify unsymmetrical, that is the easiest route. See the last group, terminal group, and find out. To find symmetrical, okay, you have to check all the groups. Okay, suppose if this is the middle, from the middle, if I go this way, I have keto here, but in this way I don't have keto. So this is not a symmetrical. So it is also unsymmetrical. If it is unsymmetrical, then the formula is 2 power n. Right? So 2 power 3, which is 8. So there are 8 optical isomers possible for fructose. For fructose, we have 8 optical isomers. For glucose, 16 optical isomers. Very good. Now, students, tell me whether it is D or L?
D, sir.
D, yes. OH group is present in right hand side. Yes, you are right. OH group is present in right hand side, so it is a D fructose. This molecule should be called as D fructose. And remember, student, these are the proper Fisher projections of the molecule. So you have to remember this. Listen, usually OH groups are present in right hand side. Okay, but in fructose and glucose, in the third carbon, OH group is present in left. See, in fructose, third carbon, OH group is present in left. Similarly, in glucose also, in the third carbon, OH group is present in left. Right? This left to right you should say only with respect to Fisher projection. In this molecule, if you take this structure, here left right is they do not have any meaning here. You cannot say that this is left and this is right. That is not correct actually. Okay, in this structure, right, this is left, that is right, that is right, we cannot say. Okay, only in Fisher projection you can say these groups are left hand side groups and these groups are right hand side groups. Okay, yeah. Okay, I stop here.